I'm Mike Rainey, and this is joint work with Umut Akar, Vitaly Aksanov, and Artur Shargaro. The setting of this work is any language or library that supports fork join, such as Cilk or Intel's threading building blocks. In these systems, we can annotate the source code to make calls go in parallel, or we can use parallel loops, and we can write programs that nest these parallel constructs recursively. The parallel computations that arise from these programs can be very fine-grained, hard to predict, and can be irregular in shape, which altogether makes it challenging to achieve high efficiency. One of the things that often gets in the way of efficiency are the overheads that come with parallel tasks. So even if parallel tasks were very, very cheap, enabling all the potential fork points in the program can come at a huge cost at runtime, even to the point of negating the utility of parallelism, or even worse. On the other extreme, we could just sequentialize the program, but that would just be giving up on parallelism. So what we prefer is some approach that can balance between these two extremes, do it consistently, and in the face of challenging irregular fork join programs. The current state of the art in this problem space involves tuning on behalf of the programmer. The goal of tuning is to coarsen parallel tasks so that they're large enough to amortize the overheads. Unfortunately, the tuning may involve searching through a huge space because any given tuning configuration is sensitive to the input of the program, also to the context in which the region of the program is running, as well as the platform in which the program is tuned. So because of all of these sensitivities, even well-tuned programs may overfit to the machine on which they're tuned. And making things even worse, generic programming mechanisms such as C++ templates make it even harder because now one region of code can easily show very different behaviors depending on where it's called from. To get a visceral sense of the problem, suppose we write a parallel loop like what I have on the top of the slide. Now, to control overheads related to tasks, at some level, we'll need a way to bunch iterations together. One common way of doing that is to use coarsening, like what I'm showing just below it on the slide. So we now have to pick the grain setting based on some tuning process, and we potentially have to worry about overfitting to machine that we're using to tune. Furthermore, we're in trouble if we want to use a generic interface, such as this map function that I'm showing now at the bottom of the slide, which is doing the same thing, but in a more kind of generic fashion. So now we have a problem because we might want to call the map function at very different granularities. So one might imagine passing the grain setting as an argument to map, but that's going to complicate generic programming in ways that we'd like to avoid. Existing work on this kind of granularity control problem usually takes one of two methods or approaches. Either you try to reduce the cost of task creation, or you reduce the number of tasks being created. So reducing the cost of task creation has received a lot of attention, and we certainly want to leverage on that work, but that path doesn't go far enough to deal with all the cases. So instead, the solution is often to try to reduce the number of tasks being created. One of these approaches is what's called lazy scheduling, which tries to amortize the task overheads against either load balancing actions or against past work. But lazy scheduling requires sophisticated compiler and runtime support, which isn't always available. The other approach is what's often called granularity control, and that approach basically uses predictions of the running time to control when the program switches from some parallel to some sequential execution. So our contribution into this granularity control space is a runtime technique that applies to a large, well-defined class of fork-join programs and ensures provably small overheads for tasks, while at the same time guaranteeing good utilization of the processing cores. Our approach is based on transferring the job of the tuning to the runtime system or to the library implementation of fork join. The component that we propose to manage the tuning is what we call the series parallel guard, or SP guard. It's a new kind of control flow construct that picks between parallel and sequential execution at runtime on the fly. The SP guard consists of a parallel body, which is a function that's supplied by a client and performs some parallel computation. There's also the sequential body, which performs a sequential computation that's semantically equivalent to the parallel body. And there's also an abstract cost function, or just cost function. So when it's called, the cost function returns some abstract measure that represents the running time of the sequential body. Here's a pretty accurate sketch of what we'd write to get a parallel merge sort with automatic granularity control. Our parallel merge sort function takes in a sequence X and returns a sorted sequence R. And its cost function reports n log n, where n is the size of the input sequence. The parallel body performs a straightforward parallelization of the merge sort algorithm. It handles the base case, and in the recursive case, it divides the input in half, recursively calls itself in parallel, and finally concatenates the results at the join point. The sequential body just calls into some sequential sorting algorithm. So using our using our SP-guard algorithm, the executable for this code has guaranteed efficient granularity control. But how does the SP-guard manage to do that, given that all it has are the cost function and the parallel and sequential bodies? So as you may have guessed, the cost function isn't going to be sufficient to make good sequentialization decisions. The starting point of our algorithm is a per machine tuning parameter that we call kappa. So kappa represents the smallest task that we want to parallelize. Typically, good settings for kappa range somewhere between 25 to 500 microseconds, depending a lot on the machine. Fortunately, though, there's a straightforward tuning process that can find a good setting of kappa, and we need to run it just once per machine. So it's a one-time per machine tuning process. Now, getting to the SP guard, at runtime, when control enters an SP guard, the first thing the SP guard does is it takes the result of the cost function. Let's name that temporary value cost. Based on the result of cost and some internal state of the SP guard, which we'll get into in a bit, the SP guard executes either its parallel or sequential body. As the body executes, the SP guard algorithm collects the total execution time over all parallel paths of the body. So if it's the sequential body, it's simple. Then we just use the cycle counter to measure the elapsed time. If, however, it's the parallel body, then we get the combined execution time across all parallel paths using a tree reduction. So let's call this process, the result of this process, the work. After we obtain the work, we try to update the internal state of the SP guard, which consists of a cell that we call cost max. The SP guard uses this cell to get better and better estimates of when to sequentialize in the future based on the current value of the cost. The invariant that we need to maintain for this cost max cell is that the cost max value, the value in the cost max cell, represents the largest cost value that's been observed so far, such that the corresponding work is marginal, or in other words, smaller than the value of kappa. We'll get to that again in a second. So finally, we have the sequentialization decision. So the SP guard uses the cost max cell to make its sequentialization decision as shown at the bottom of the slide. It just says that if the current cost is less than 2 times what's the current value of cost max, then you sequentialize, otherwise you parallel. The description of the algorithm that I'm giving here is a bit simplified with respect to what's in the paper, but it has all the main ideas. So each SP guard initially starts out with its cost max set conservatively so that everything is parallel. As the program runs, the SP guard increases the size of cost max using an exponential growth rate. The growth continues until the value of cost max converges to a size that corresponds to tasks of approximately kappa size. And we have a proof in the paper that the convergence is guaranteed and in a bounded amount of time. What the graphic in this slide is showing is approximately what's going on with that cost max that cost max cell. So for a given SP guard, we have we're showing essentially this this green line getting closer and closer to convergence with each report, which is kind of represented by one of those dots along the line. So we have these over time. We have these SP guard executions, which are taking measurements, updating the cell of cost max, increasing its value until it gets to just the right point, and then we have a stable convergence. So that's essentially what's going on. Now I'm going to get into the main theoretical result of our work. To start, let's review the work span cost model, which consists of 2 metrics. The work represents the total amount of computational steps performed by the program, and the span, the length of the critical path in the computation graph. So using this cost model, Blumoff and Leiserson proved a classic result for the work stealing load balancing algorithm. The bound that they proved states that the running time of a fork join program using work stealing is bounded by the work divided by the number of cores plus the span. The bound is an expectation because it's a randomized algorithm, but what's important about the bound is that it accounts for the overall cost of load balancing, and it tells us that work stealing achieves a linear speed up when the W over P term in the bound dominates. However, the bound assigns a unit cost to the creation of a task, and therefore says nothing about the overheads of task creation. So to get a bound that accounts for the overheads of task creation, we're going to assume that the load balancing is performed by work stealing, even though the bound that we show in the paper is a more general bound, which is actually compatible with any load balancing algorithm. So to model the cost of creating a task, we use a parameter called tau. And for the purposes of explaining the bound, let's just assume that our tuning process gives us a value of kappa such that kappa is a factor 20 of our tau parameter. So in other words, we're picking our marginal parallelism to be 20 times larger than the cost of a task. Okay, so now looking at our bound, which is at the bottom of the slide, there are three new terms relative to the original work-stealing bound. The first of these new terms is basically telling us that if we pick kappa to be factor 20 of tau, then we can expect to add about 5% in the worst case to the, we can add about 5% overhead cost for the tasks. The second term is telling us that we're increasing our span by a factor 20, which is effectively decreasing the amount of available parallelism in the program. It might look like a lot, but it's actually not a problem in practice, because the parallelism that we're eliminating is tends to be parallelism that's too small to take advantage of anyways. And finally, the third new term in that bound represents the cost of convergence for the cost max term in the SP guard. So this term essentially is negligible cost at runtime. So overall, we have one new term that's telling us we have a bounded cost for tasks. We have another term that's telling us we have some reduction in the amount of available parallelism, in our program, but we're only decreasing the amount of available parallelism by a small constant factor. And then we have one other term that's telling us that we have a cost to pay for the convergence of the SP guard, of the cost max cell in the SP guard, but this cost is a small bounded amount. So we implemented our algorithm as a C++ library consisting of some functions for SP guards, some frequently used cost functions, and an assortment of data parallel operations. Our library uses Cilk, but in fact any fork join language or library extension is compatible with our implementation. We ported 8 benchmarks from the problem-based benchmark suite, which is a collection of algorithms that represent various problem domains and feature some irregular workloads which are particularly challenging for granularity control. The majority of our porting effort consisted of replacing the sequence library of the problem-based benchmark suite, which is used by most of the benchmarks in the suite. This sequence library implemented data parallel operations such as map, reduce, filter, scan, etc. by versions that use our automatic granularity control. And so overall, the porting effort was straightforward because in most cases, the operations we replaced had some straightforward linear time cost functions for which we could just use the same default call to an appropriate size function. Over the hundreds of lines that we ported from the problem-based benchmark suite, we wrote just a total of 24 SP guards and their associated cost functions. Otherwise, managed to use our default cost functions. Or on the other hand, the original PBB or the original author's code of the problem-based benchmark suite used 5 different kinds of manual coarsening techniques and heuristics to do the granularity control. So overall, we were able to replace this variety of manual techniques with one uniform automatic technique. So for our experimental evaluation, we benchmarked the codes that we ported and used the original version of the codes as the baseline measurement. in our experiments. So the plot here shows results on our 40-core test machine. In the plot, lower is better for our technique. The main result is that our automatic granularity control matches the performance of the author's original code, which is using this mix of 5 different kinds of granularity control manual techniques. It in that sense simplifies the code, and it also brings portability across different machines. We've independently checked these results on at least 5 other very different machines and gotten similarly close results in terms of performance. We also have some additional results in the paper that aren't shown in this plot, coming from a BFS, a parallel breadth first search benchmark, where in the original author's code there was an inner loop that was serialized in order to avoid poor performance that was being observed on certain input graphs. Now the results of that study are showing basically that our automatic granularity controller basically enables safely parallelizing that inner loop that was kind of conservatively sequentialized, and basically comes at no cost for the graphs that had previously been problem cases, and in some other cases improves the performance when there are graphs that can benefit from the additional parallelism that can be exploited by that inner loop. Now, finally, I'll just conclude with covering the main results of this work with respect to the related work. Now, I'll just divide the related work into 3 kind of broad categories. The first of which concerns proving bounds for load balancing algorithms. Now, our result extends these existing bounds, such as the bound we saw for work stealing, to account for the critical overheads of parallel tasks. Now, in the second category of related work, we have approaches that correspond to lazy scheduling. So recall that these techniques basically try to amortize task overheads against either load balancing actions or recently performed work. Now, we believe that this technique we've developed is largely complementary to this work on lazy scheduling. On the one hand, the technique that we've developed brings the advantage that it can safely switch execution from parallel to sequential and effectively use faster sequential algorithms close to the leaves of the computation tree, of the call tree. Whereas in the case of lazy scheduling, you have to basically have the parallelism always on, and in particular pay some overhead to do the checks needed to test when task overheads have been sufficiently when tasks are effectively amortized. So our technique can be viewed as an improvement into in this space that can potentially allow safely using faster sequential algorithms in certain parts of the program. And there's certainly a a good amount of room for future work to investigate synergies between these two approaches. Finally, there's the body of work on granularity control. So to this category, our approach adds the first implementation that's backed by end-to-end bound on the execution time, and an empirical study that looks at a collection of modern, challenging fork join algorithms. Thanks for your attention.